talking about the fine-grained complexity of the task of direct access for conjunctive queries with aggregation. I'll explain what all of that means. So this is ongoing work, so I'm telling you in advance that there's a lot we still don't know, but I'll tell you about what we do know. This is joint work with Idan Eldar and with Benny Kimmelfeld, and also Idan is going to talk about this in just a few months in ICBT. So before anything else, let's start with a motivating example. Okay, so let's say we have some sort of online platform, and we have people who contribute to create some resources, and then we have another table that tells us how many views each resource received in a day. And let's say we want to get a sense of to how many views a contributor contributes. Okay. So to get a sense of when we look at a specific person, any person, what's the impact, what's the number of views that he contributed to in some way. Okay. So how would we go about doing this with the information we have here? Well, we probably want to create this sort of table of the sum of views per contributor. And how we would do that? We can have this, I have this query as the sort of conjunctive query-like notation with aggregates. So we want to join the tables, and then we want to sum over the views, and then the contributors. So to compute this, what we can do is first we join the two relations, then we group by the contributor, and then we sum in each the views in each group. And afterwards, we probably want to sort by the views. Okay. So let's say we have a lot of contributors. We have a huge table. What do we do with this table now, right? We're not going to look over all of the rows. So maybe we want to know what's the median number of views. Maybe we want more than that, a box plot. So in addition to the median, we want the minimum, the maximum, the other quartiles. Or maybe we want some sort of histogram. So we have the bins of the number of views. We want to know how many contributors fall within each bin.
Question? Just a
Yes.
clarification question. Each view is associated with only one contributor. We're not sharing the weight of the views amongst multiple contributors?
If I understand your question correctly, you mean like if two people contribute to one view, I'm going to count the view for both people, like an entire view for both people, right? Yes, so that's what I do. Okay. I just want to know in how many views you impacted in some way. I don't want to quantify your exact.
It's not a flow rate kind of thing. It's
yeah. For this, I think Benny worked on this type of question of, and maybe he's going to mention this in his talk on Friday. I don't know. Okay. Right. So what's the complexity of what we just described? How long would it take us to do all of this stuff? Well, the expensive component here is actually the join, right? If we're joining two relations, it's going to be a quadratic time algorithm. The output of the join can be quadratic, and then everything else is more or less linear in the result of the join. But if you notice the amount of like actual information we need for these things, it's not a lot of like pieces of information. So what we want to know is whether we can compute these things without actually materializing the entire join result, but sort of get these things immediately directly and save a lot of time. And well, yes, we can for this query and also for queries that are more complicated, but not always very efficiently. And this is what I'm trying to explain in this talk. So more specifically, the query answering task we would be considering is ranked direct access. So what this means is that we want to simulate a sorted array that contains the answers. We would have some sort of data structure that receives an index and return the answer in this index. And the ranking is specified by the user along with the query. So what this means is that if we have this sort of standard approach for query answering, that we have an algorithm, we specify a database, we get the query answers. Here our approach is different. The algorithm doesn't immediately produce the query answers. It produces this sort of data structure. You can call it a factorized database if you want. And then you can ask this sort of access calls of this data structure and get the answers in these indices. Okay, is that clear? Now, why do I think that this task is so interesting? Because it can be used to solve many other tasks that are quite common. So first of all, we can use ranked access for quantile computation and for computing histograms, which is what I mentioned before. Second of all, we can use ranked access to get pagination. So basically, imagine you have a lot of answers. You want to show the first page of the best answers, and then you want the user to be able to click to go to the other answers. This is like offset and limit, basically. And if you have ranked access, you can do it more efficiently than what's typically done without actually producing all of the answers first if you want a specific page. And this is equivalent to ranked access, actually, in a way, because if your pages are of size 1, if you're allowed to choose that they'll be of size 1, then this pagination is exactly ranked access. What else we can do? Well, we can do ranked enumeration, which is what Nikos was talking about in the previous talk. If you just access the indices one after the other, 1, 2, 3, 4, and so on. And then there are also things you can do that are regardless of the specific ranking you use, even if you don't force a specific ranking on the simulated array. So first of all, you can do counting if you just binary search to see when you get out of bound. And you can also use direct access to get a uniformly random ordered enumeration, which is sampling without repetitions. The citation here in case you want to see how this transition is done. And of course, if you have enumeration, then it just gives you a way of producing all of the query answers if this is what you want. Okay, questions so far? Good. So the question that we're going to be asking, well, ideally what we would want to know is given a query in an order, what's the best algorithm, the best complexity we can do to solve this query in terms of fine-grained complexity. And as an intermediate question, we would like to ask which queries we can solve with the ideal time guarantees. So quasi-linear preprocessing, so linear preprocessing in constant time per answer would be the ideal, and let's allow some logarithmic factors to be able to actually do stuff. And the focus in this talk would be for conjunctive queries with aggregation and lexicographic orders. Okay, so this was the motivation. And let's now tell you about a little bit what we know about this. So first, let's mention what happens for conjunctive queries without aggregates. I'll just briefly mention what we know without going into the details. So when we have a conjunctive query without aggregates, and we have a specific lexicographic order we want to achieve, so we have an ordering of the free variables of the query, we can do that efficiently, exactly in the cases where, so first of all, the query has to be acyclic, the same definition of acyclic that Nikos was mentioning in Fokyon. So this is what we need even just to enumerate the answers of joint queries. It has to be free connex, which means that, so definition of acyclic is having a joint tree, a free connex query. On top of being acyclic, it needs to also remain acyclic when you add another hyperedge that contains exactly the free variables of the query. So this means that the projections behave nicely. And then we have this extra condition that tells us that the lexicographic order we want to achieve is something we can achieve. So this is equivalent to saying that the lexicographic order is the reverse of an elimination order, for those of you who know what it is. But if you don't, there is like actually a condition that's quite easy to understand or verify that tells us what are the interesting orders. So the good orders are the ones that don't have a disruptive trio. So a disruptive trio is 3 variables, such that the last one in the order we want to achieve shares atoms with the previous 2, but the previous 2 are not neighbors. They don't appear together in an atom. So here are examples. And And in my notation here in the slides, the order where I put the variables in the head matters. Okay, so here I specify a conjunctive query, and I also specify the lexicographic order that I want to achieve. So these are both the same query, but with different lexicographic orders. And you can see that the first one has a disruptive trio, so it doesn't have efficient direct access, but the second one doesn't. If this holds, we have an efficient algorithm. If this doesn't hold, we have a hardness proof. This hardness proof, like all hardness proof in the RAM model, requires some assumptions, but I don't want to spend too much time on these assumptions. It's very similar to assumptions that were used before for similar problems. And also, if you heard me talk before about self-joins and how much they cause problems in the complexity analysis of enumeration, it's not a problem here. Actually, we can show that the complexity remains pretty much the same up to logarithmic factors even if you have self-joins. Okay, so this was without aggregation. Now what happens when we want conjunctive queries with aggregation? So our idea is, surprise, surprise, use semi-rings. So we translate the aggregations to semi-ring, and you can see here an example. This is what we want to solve. These are the answers you're expecting to get. This is the array you're trying to simulate. And the way we would solve it is basically we want to sum over W. So we add annotations to our tuples. And then on the table R that contains W, the annotations would be the value of W. And then we use a semi-ring where we would basically sum up these W values. So the answers to this query over this annotated database would be what we're trying to get, basically. So now we're using annotations, but how do we solve the query with the annotations? So first of all, we need to handle the projections. So in this case, we don't want the W value, so we need to get rid of it. So we project in R, and then we sum over the annotations. And then once we eliminate, and in general, whenever we have queries that are cyclic and free connects, we can do that efficiently. And then once we have a full conjunctive query with annotations, we use the direct access algorithm that was known for conjunctive queries. This algorithm tells us, we just ignore the annotations for now. This algorithm tells us the assignment for X and Y. And this tells us which tuples we need to take from each relation. So now we look back at the annotations, we multiply them, and we get the answer we wanted to get. So actually using these semi-rings and this idea of annotating the tuples, we could support this quite elegantly and efficiently. So this was one example. In general, we have a dichotomy that tells us that whenever we have this query with a lexicographic order, where we want to get an annotation at the end of the lexicographic order, so the annotation doesn't affect the ordering in the simulated array, then the tractable cases are exactly the same tractable cases we had before. It doesn't cost us anything to add this aggregation. Right. So I guess you all know in general what commutative semi-rings are at this point. We need the operations to be able to be calculated efficiently in up to logarithmic time for our analysis here. And we have, of course, this approach we saw before, where we annotate tuples with a semi-ring element. When we use tuples jointly, we multiply the elements. When we use them, we have a choice, then we use the addition. So what kind of things, what kind of aggregates can we solve in general on top of this specific example I showed you here with these annotations? So we can very easily support sum and count using the semi-ring where summation is summation, multiplication is multiplication. And we can easily support min and max using the tropical semiring. Now, what happens if we want to solve other common aggregate functions? What are other common aggregate functions? So, for example, average. We can also do that efficiently by just accessing an answer and computing its sum, and then accessing the same answer and computing its count, just the same way we did before as black boxes, and dividing the two. So we get the average. Yeah.
Do you mean by a log time commutative statement?
I mean that the operations can be done in up to logarithmic time. Right, so this was average. And then anyone wants to guess what the other aggregate that I want to support? Sorry? Median. I do, but as Nico said, like we don't even know how to do it for more simple things. But if I'm thinking of things that people usually use, like in SQL and stuff, well, there's count distinct. So count distinct, there's no semiring translation, so we can't use the same approach we had so far. And then the question, oh no, spoiler. And then the question is, do we just need a different approach to solve this and get the same guarantees, or is it really harder than the other aggregates? And then we found out that it really is harder than the other aggregates, and you can see it on this example here. If you replace count distinct with any aggregate, any other aggregate we mentioned, this is easy because it's a cyclic and free connex and with no disruptive trio, so according to what we said before. But with count distinct, we have evidence, we have a proof that shows that it is actually hard. But our proof uses the fact that Z, the variable Z needs to be able to have a very large domain to get assigned a lot of, possibly a lot of values can be assigned there. And if you happen to know that the number of possible assignments to Z is small, it has a log size domain, then actually you can do count distinct efficiently by just using the set semiring and computing the set of all values that Z can get. And then at the end, you just take the size of the set. Okay, so this was what happens when the aggregation doesn't affect the order. Now what happens in the more complicated case when we want the aggregation to be able to affect the lexicographic order. And I'm going to just give you a sense of the type of thing we find out using the examples. So the first example is like what we saw before. The annotation is last in the lexicographic order, and the annotation is actually a function of the x and y values, which means that it doesn't affect the order at all. And we saw that this is tractable for this query, because it's a cyclic and free connex and with no disruptive trio. Now, what happens if we want the annotation to be first in the order? Well, it turns out that this query is hard. We have a proof that this query is hard, assuming the well-known conjecture threesome, which is really bad news because this is quite a simple query, right? We would want to support that efficiently. Okay, what can we still do? Let's say the annotation is in the middle. Is it still hard or is it easy? What happens now? Well, it turns out that it's easy. We have a result that tells us that in general, whenever an order can be solved efficiently when the annotation is at the end, we're allowed to push the annotation one position backwards. So we're allowed to have one variable after the annotation, or a set of variables that behave like one variable in a way. So this is easy. And at this point, we say, okay. So here on the slide, we have one thing that's hard and quite simple, which is a shame. We would still like to be able to do things like this. What happens when we have this sort of aggregate queries that we would naturally translate to this hard query Q2? So Q4 here, using the same kind of translation to annotations I showed you before, we would want to solve Q2 for it. If Q2 is hard, does it necessarily mean that Q4 is hard? Or do we lose some efficiency in this sort of translation to aggregations? Now, you can notice here that in this translation, only the relation R gets interesting annotations. Since S doesn't contain W here, it always contains 1. And in our hardness proof using threesome, in our construction, we had to put in S like different interesting annotations. So this doesn't necessarily, it's not necessarily as hard as before, and actually it's easy. So the way we can solve it for this query, we can just imagine here we have another variable, introduce another variable. This would be another column in our table. And then we get the query here. That's a cyclic and free connex and with no disruptive rules. So this query can be solved efficiently, and our example is easy. And we were able to show that it's easy by going through these annotations and then getting rid of the annotations. But because the annotations are local, they only appear in one relation. We use this fact. Now there's just one more thing I would like to mention here, is that here in this new R, this column that we introduce, we have a functional dependency. So for each value of X, we will have one value of Z. And this is something we can actually use to get more tractable cases for direct access. So in this particular case, we didn't need it because the query is already of a good structure. But in general, we know that functional dependencies can help us get more tractable cases. And also when we use it with local annotations here in this context, functional dependencies sometimes help. Okay, so when we have local annotations, we have full characterization in some cases to know when these local annotations can be solved efficiently, and in the other cases they cannot. But maybe since I don't have a lot of time, I won't spend too much time on explaining this. Right.
What does hard mean again? Do you have a lower bound or?
Yeah, hard means a lower bound. It means that I have a conditional lower bound, a proof that says that I cannot do direct access with quasi-linear time to build the structure and then logarithmic time per axis. Last example, I think it's the last example I wanted to show you. So here Q4 is easy. Q5 is another query that if we translate it to our annotations, we would get Q2 again. But in this case, since it's something that, in this case, we don't get the annotations, that the annotations are local. And so the question is, again, does it mean that Q5 is hard, just like Q2, or can we somehow solve it in a different way? And actually, we show that we can solve it in a different way. We have an algorithm, but this is quite ad hoc. So I don't know how much it extends, but this sort of tells us that this annotations approach lead us very far, very elegantly to be able to support a lot of things. But this is sort of evidence that maybe it doesn't cover all of the efficiency that we can get in general. Okay, so to conclude, I spent quite time trying to convince you why I think that ranked direct access is a really cool problem, because it can solve, it can help you find box plots and histograms and pagination and a lot of other tasks. Then we saw the dichotomy that we have for conjunctive queries without aggregation, and then we used this dichotomy to introduce a similar dichotomy when we also have aggregation, but the aggregation doesn't affect the order. And then we saw that when we want the aggregation to affect the order, we hit interactability quite fast. And interactability is a big word, right? I just mean no quasi-linear preprocessing and logarithmic access time. So we hit that very quickly, but then we can still get some more tractable cases by looking at local annotations and sometimes in other ways. Okay, future work. So first of all, as I said, this is ongoing and there are open cases and things we don't know how to classify. Regarding self-joins, so self-joins is when you use the same relation in different atoms. So for the dichotomy without aggregation and when the aggregation doesn't affect the order, this actually holds just the same if you have self-joins or don't have self-joins. We have a proof for that. But when aggregations affect the order, then self-joins actually make things complicated, and all of our results are without self-joins. So it would be interesting to look at that and see what happens there. And in this talk and in this work so far, we only looked at whether we can do things with only quasi-linear preprocessing. What happens to the cases where we can't do that? Well, we'll be willing to pay a bit more because we don't have another choice. But how much more do we need to pay? This is a question that we still need to ask. If our queries are only join queries, and so without projections and without aggregations, then we know exactly what happens for lexicographic orders. If we want to achieve logarithmic access time, we know exactly what's the pre-processing time we need, and we have a conditional or bound that tells us that we can't do it with less time. But already if we introduce projections, we don't know. We know that there are things that are more efficient than the trivial thing you would try to do with like using a decomposition and so on. And of course, there is we can make it more complicated in many ways, more complicated orders, more complicated queries, maybe try to support updates over the structure and so on. And this is all I prepared for you. Thank you.
Questions? In case of count distinct, what happens if you allow approximation?
Well, I don't know. That's the correct answer. For count distinct if you allow approximation. I don't know.
There are sketching structures for such things, right?
Yeah, but they require randomization. So I just wondered.
Yeah.
I'm a bit unclear why you say log time and not log space. Do you mean in log time over numbers represented in log space? I mean.
Right. So we're using, well, I wasn't very specific about the model and computation of everything. So we're using the RAM model where the words or the registers are of logarithmic size. And typically we assume that the operations take constant time. So summation and multiplication over these registers would take constant time. But actually for our results to hold, it would also be okay if the operations take logarithmic time in the size of your database. And we use it for what we say about count distinct. So if you want...
The number of registers is a constant?
The number of registers in what is a constant?
How do you, when you use the calculation for using the RAM model, you just use a fixed number of registers, right?
So, I mean, if you're looking at your memory can be of polynomial size. It needs to contain your input and then other things, and then each memory cell is of logarithmic size. So you can store, elements that you need a logarithmic number of bits to represent, basically.
Good. So then let's take half an hour break and then come back and continue our open discussions. Okay. Thank you.